So we want to know about the remainder story for the quadratic Taylor polynomial. We want to be able to say something more than simply f of x is approximately t2 of x. So the thing to ask is, why isn't it perfect? We have some function f of x here. We have its Taylor polynomial. I guess use the right color. Why aren't they exactly equal? Well, remember what's special about t2 is that it's since it's a quadratic, its second derivative is constant. We saw that in the calculation. That's a pretty standard thing. Quadratics are things whose second derivative is constant. They have a constant concavity. And f of x probably doesn't have a constant second derivative. But what measures the change quantitatively in the second derivative? It's the third derivative. So the fault lies in the third derivative of x. In particular, if you were so lucky to have the third derivative be 0, then the thing would be a quadratic. It would have constant second derivative, yep, and it would be a quadratic, and we'd have a perfect approximation. Okay, so let's assume, and this is something that we're going to have to, in a particular problem, this is where we'd have to do the work. Let's assume that we know that this is less than or equal to some m. So we're going to reuse that letter m. It's going to be a general letter for a bound on a derivative, or the size of a derivative. So we're going to assume that we've looked enough at f triple prime. We don't know it exactly, probably, because the whole point of this is we don't understand the function very well away from the base point, or we don't want formulas that involve complicated calculations away from the base point. But we have some sort of universal number that bounds the size of this. Well, I don't want to say universal. Again, I want to, it'd be too ambitious. Almost always it's too ambitious for that to be true outside of some predefined safety zone. So let's say and we'll do this explicitly if you're worried. Let's say we can find this bound for all x with, and you usually see it written as the distance from x to a is less than or equal to d, just like we saw before. Or in other words, if you like it as inequalities, it's just everything in this interval. Okay, or you could even say x is in, ooh, that's getting away from me here, the interval a minus d plus d. Okay, so let's assume that that's known, and let's see what we can do with that. So, let's see. Fortunately, I'm gonna have to erase it right away. Okay, we're gonna back to it. So we want to analyze the remainder. So what do we know about the remainder? Okay, that is the real thing minus all this approximation. And so it's f of x just minus the quantity, all this stuff. I don't think I'll write it out. And there's some really nice things we know about that function. And then I'm going to look, based on that, what we know, and then I'm going to look at some worst case scenario stuff. And this is a pretty good way to analyze inequality conditions, is look at the worst case scenario. I want to notice that R2 of A, everything's nice at the base point. R2 at A is just 0, because that's where f of A and T2 of A were 0. We're the same. R2 prime at A. Remember, one of the nice things about T2 was its derivative at A and F's derivative at A were equal. So this guy has 0 derivative. And the same thing was true of the second derivative. The whole point of choosing R2 the way we did was to make the second derivative of F and the second derivative of T2 at A, not necessarily anywhere else, but at A, they were matched. So R2 is a function that's really, really nice at A. And that's going to be really helpful. Okay, but, okay, then what about this condition on the third derivative? Well, there's something really nice about the third derivative of the remainder. Make that look more like an R. What you're subtracting off is something whose third derivative vanishes. A quadratic function, you take 3 derivatives of that, it is 0. And so the third derivative of R2 is exactly the same as the third derivative of f. So it's not 0, but it's nothing new. So in particular, the size of that is the size of this guy, and we know something about that. This is a very common technique. We're trying to analyze how two things relate to each other, f and t2. In order to do that, we subtract one from the other to compare them explicitly, and we get something that has some of the features that we had in f here, this bound, and then some other really nice simplifying features. So we just want to see, how big can R2 get? Remember what happens as you go away from A, where R2 is 0, we just want to get a bound on how different these things are, how big R2 of x can be, as long as we stay within our safety zone here. We want to get a bound on how big a function with these properties can be. And that's where it's really good to look at the worst case. So I'm going to look at just one worst case scenario. If you know that this mystery function has a third derivative that's everywhere less than or equal to m, then the way it's going to grow fastest is if you peg that third derivative at m. Now you could peg it at minus m as well, and it'll go negative as fast as possible. But just to be specific, the signs can be a little annoying. What we're going to do is we're going to just look at one side. We're going to look at where x is greater than a, or in other words, we're going to stay in our safety zone. We're just going to look at those x's, like over here. And we're going to say the worst case scenario is where this remainder function actually has third derivative always equal to m. It takes advantage of all the turning away from a quadratic, upward away from a quadratic that it can be. And m here is always going to be a positive number. Okay, you know what? This is something we can just do antiderivatives on and get an exact formula for R2. So let's do that. As usual, I'll go up here. I don't really need the title anymore. Okay, so R2 triple prime, we're going to assume it's this constant m. And we're just going to do 3 antiderivatives, and they're not going to be hard. R2 double prime, okay, the antiderivative of a constant is just a linear function. Okay, and we want to make sure it's a linear function that vanishes at a. Oh, there's an easy way to do that. It's just going to be R2 double prime has to have slope m, so that its derivative is equal to the constant m, and it's got to vanish at a. So it's going to be m times x minus a. The fact that x minus a shows up all throughout this is something I've talked about before. You want to keep everything in terms of x minus a in this business. Okay, so that's good. We've gone one level up. We now know in the worst case scenario what R2 double prime is. Okay, and let me sort of give a picture for that worst case scenario. Maybe f of x really is like this, but what we're saying is that given the bounds we know on f of x, maybe it's kind of going up like this, and we're kind of getting, what's the worst case scenario? We could also do a worst case scenario of like how small it could be, and we'll get it bounds in between, but we're going to look just at one side, just for simplicity. So that's one of the pictures you might want to have in your head. So I want to know, what is the antiderivative of a linear function that vanishes at x equals a? Not hard to do. That's a quadratic. As long as you do it in terms of x minus a, that automatically satisfies the initial condition. You can check. This is a function whose derivative is this. It's easy. And such that vanishes at a. So we checked. We've used that condition. We've used that. And we've used that. And you might notice, this looks really familiar. That looks a lot like this. And there's this nice connection between the terms in the approximation and the error bounds in the next approximation. Okay, so R2 of x itself, we just want to do one more antiderivative. The antiderivative of a square is a cube over 3. I've already got a 1 over 2, so that's a 1/6 m x minus a cubed. That's really the key calculation here. So again, I'm not saying that the remainder is always equal to this. I'm saying this is all the worst case scenario. And the great thing is, if you know the worst case scenario is an equality, you can just change those equalities to inequalities, and you've got the general statement. So now I can finally get rid of this. And what we've got is that in any case, not just the worst case, R2 of x is less than or equal to 1/6 m x minus a cubed Now, that's as long as I didn't go past a plus d. Because once I go past a plus d, that fundamental assumption that the third derivative was less than or equal to m doesn't necessarily apply. That's where I knew that. So far, I've only done it going off to the right. But it's totally symmetrical in terms of going up or down, left or right. You just have to put absolute values everywhere. In general, the size of that error of the quadratic approximation is less than or equal to 1/6 times that magic number m that we might be tricky to get because it's something about bounds on the third derivative, times the absolute value of x minus a cubed. And there's our error estimate, or error bound, actually, for the remainder, the error in the quadratic approximation. As long as you know something about the third derivative, you're going to be able to get m, hopefully. You divide that by 6, which I'm going to give a big hint. That really came to us as a 1 times 2 times 3. That's called 3 factorial. That's a big hint as to what might come next. And then times x minus a, absolute value of x minus a cubed. Notice, as usual, when x equals a, this is 0 because R2 is exact at a. And it grows as x minus a increases. But another way to say it is that as x minus a decreases, when you take x closer and closer to a, that cube is a really good thing. When I have x minus a, when I go twice as close to a, this is going to go down by a factor of 8, and that's a really good sign. And that's what you refer to as like a third order approximation, something that when you take a certain parameter, if you divide it by 2, if the error bound goes down by 8, that's a good thing, and that term third order is usually used in that case.